about this is that if you look at coefficient of lift, here's what you might see, something like this. This is coefficient of lift versus angle of attack. And angle of attack, again, in terms of a sail, we'll keep things into a sail. So you have a sail that looks like this. And so if you look at your boom, and this is your mast up here, and this is the sail here, this is the boom down here. If you look at the relative wind direction here, then this angle here is called an angle of attack. Well, let's call it alpha. Angle of attack. And so what you'll see is that most wings will have a pretty straight line for coefficient of lift versus angle of attack. If you double the angle of attack, you'll double the lift coefficient, which doubles the force. Now, this is for a rigid wing, and of course for a soft wing, it's not quite the same thing, because at low angles of attack, you get what's called luffing, and you don't really develop any lift at all. So unfortunately, for a single surface wing, this doesn't really follow that very well. It's going to be more kind of like this. Like there's nothing until you reach an angle of attack, and then you'll get that coefficient of lift. Okay, what happens at this point here? What happens over here with the wing? You have a very high angle of attack in degrees. This would be like, maybe for a typical airplane, it might be like, say 18 degrees. That might happen. What happens?
You stall.
Yeah, stall. And so stalling is not like a car. It doesn't mean your engine stops. It really means is that you've got such a steep angle of attack that the flow can no longer stay along the upper surfaces. If you don't understand that, this is very primary for, I'm sorry for you engineers that MEs understand that, is that when you develop a wing, there's a pressure profile that looks like this, where this is a low pressure area, which by Pascal's law? No. The law says the pressure is always normal to the surface. Force is exerted by pressure. I think it's Pascal. I think it's Pascal. Anyway, so this is a low pressure area that develops when you have across a wing. And there's also a teeny bit of high pressure here. But unlike, it may be counted, not intuitive to most people understand wings, but the upper surface of the wing is where your lift comes. There's a teeny bit from the bottom, but it's got a little higher pressure here. But really, it's the upper surface which develops the lift. And so on a sail, it's this part here that's important. This other side doesn't really do much. In fact, on a single surface wing, it doesn't do anything. You can put anything you want there, it doesn't affect the lift of the sail. And it's the reason, by the way, why you'll see with only one exception I've ever seen, on aircraft, military aircraft that have weapons and stuff, they always hang them underneath the wing, never on top of the wing. Because underneath the wing is not a big contributor for lift. It is for drag, but not for lift. If you put something on top of the wing, then you screw up the whole lift of the wing. And so similarly, it's the curved surface, outer curved surface, which forms the force of what you want to do for creating lift and sailing. So, anyway, so we have this sort of stuff, and so we can actually think about, the force being a little differently here when it comes to sailing. You can think about it as being you can call it some of the different things. We'll call it C prime, which is actually this slope. And then that would be times alpha, which is the same thing as here. And so if you increase angle of attack, you'll increase the lift. But then again, as I said, this is more like for airplanes, but for a sail, it's more like this, unless you have a rigid wing like we have on Sailbot. If you haven't seen that MQP, rigid wing, so it does follow this curve. The more angle attack you have, the proportionally more lift you develop until it stalls. And stalling is something that is interesting. How do you know if a sail is stalled? What's your indicator of a stalled sail? What does the sail look like? It looks perfect. The sail will look perfect shape when it's fully stalled. But how do you know it's stalled? Come on, these sailors must know how to know if a sail is stalled.
Just go slow.
Pardon?
You just going slower.
Yes, but again, Okay, sorry, this draws you. I thought this would be, I thought you guys would have all gotten this part here. So here's the boat here, and we're gonna put the boats under here. Okay, and we're sailing, wind's coming like this, and we're going this way. What are we looking at?
Is it luffing?
Ah, that's the opposite of stall. On the luff means you've come too close to the wind, and now you don't get this nice big camber shape. You get a softness here at the leading edge. But a stall is harder to determine because it always looks the same shape. But you're way over here to where you're having much lower coefficient of lift, which means much lower force. You guys know what telltales are? What are they?
They're like little ribbons or
Yep.
whatever you want.
You have yarns
on
like
the
this
back ears.
attached here, and you can have them kind of stream back there. If they're doing this, that's called trim. If they're doing this, that's called stall. Because that means that the wind's coming like this, now it's actually backflowing here. And it can no longer stay attached. So you gotta be really careful with sails to prevent stalling, but you will not see it by looking at the sail unless you see tailtails. And the other way you can do it if you're good is just by, if you have a wind vane on top of the mast, you can tell the angle, oh, that's gotta be stalled. And what most will do, and for beginners this is really important to understand this, is when in doubt, let it out. What does that mean?
If you don't know where the wind's coming from, like you said.
And yes, because if you're not sure if the sail is trimmed the right way, and you're not sure that it is stalled or not, ease the main sheet, which will cause the boom to swing out, until it starts to luff, and then bring it back. Because a luff, which is when this thing gets really soft, is very apparent. And the boat, you're going to be down in this area here, which normally with the rigid wing would be fine, but you're up here to the point where it's not going to work well at all with the soft sail. Okay. So we're going to talk specifically about trimming hulls and trimming sails in a later session, but I just want to introduce this little concept to you. Today's the big thing today, other than understanding a little bit about the forces here. Oh, and by the way, just for those who want a cute figure here, this can all come into an engineering term, which I hate, which says that the force is going to equal 0.0034 times the area of your sail times v squared, where this is in square feet, and this is in feet per second. No, this is in, wait a minute, this is in knots. And so this will give you pounds. And so just for kicks, I was looking at my 470. If you do this, and it has 140 square feet of sail, and say you're doing in a 10 knot breeze. 10 knots is around 10 knots, that's 11, excuse me. Let's just say 10 knots, okay. You do all that. Yeah, I think I have the figures out here. It's like about 40, 50 pounds, something like that. Oh no, yeah, it's the v squared, so this comes out to be 100, right? So, yeah, if you do all that, this comes out to be 48 pounds. So, just for kicks, that's how much force the wind is providing at 10 knots on a 470. And of course, if you're going 20 knots, what happens to that wind? I mean, if the wind is blowing 20 knots, how much is the force? 4 times that, almost 200 pounds. But it's a v squared. You double that, you 4-fold increase this. MEs, quickly, what's the formula for power if you have force? Equals force times what? Times what?
Velocity.
Yeah, times velocity. So how much power? How much power, let's say that the boat is moving, I don't know, 5 knots. How much power is being developed by the sails? If you do this stuff, 48 pounds, let's see, 5 knots would be about 8, 9 feet per second. Let's say it's 10 feet per second for kicks. That's 480 foot-pounds per second. How much is horsepower? 48 times. Am I doing this right? Let's do it quickly in my head here. Oh, I was saying, let's say the boat's going 10 knots. That's what I did. I did 10 knots. That turns out to be about 3 horsepower. Do all the calculations. That's basically what they can do. In fact, if I did the figures a little bit more thoroughly, and we talked about the big boat that I had, that had about 1,200 square feet of sail. You can develop about, in an ocean-going breeze of like 20 to 30 knots, you can develop about 1 horsepower for every 10 square feet of sail. Which calibrates right, because my 52 had no problems doing 10 knots under sail. But I had 85 horsepower diesel, I'm only do 8.5 with the diesel. And under sail, I had no problem doing 10 knots. In fact, we would do 13 occasionally. And so that does compute. But that's how much power that sail's putting out. So on a 470, somewhere between, you're sailing somewhere between, 1 and 5 horsepower is what you're normally going to be actually using. So we had an outboard on there, that's how fast we could traditionally go. Okay. Those are just kind of interesting things. So I just discovered this kind of formula. I think it's kind of interesting, but it's one of those stupid formulas which combines a whole bunch of parameters here and makes some estimates on the coefficient of lift for typical sails, which is typically about 1.5 to 2 for a soft sail, about 2.5 for a rigid sail. Okay. This formula works the same whether you're in air or water. What's the difference in density? What's the difference in density between air and water in a factor? Anybody have a clue? Obviously, water's a lot denser. How much? 100? 1,000? Which is it closer to? 1,000. It's 800. It's like 800 times. Okay, and so if you put that in there, and you put a bunch of other stuff in here, it seems like, well, remember, the keel, or your centerboard, whatever, has to develop the same side loads as your sail does. And yet, certainly, the area is not 800 times smaller. But remember, the velocity you're dealing with, the fluid here, is now the boat velocity, which may be 3 or 4 or 5 knots, versus the wind velocity, which may be 10 or 15 knots on the sails. So that's one reason why it's different. And the other thing is that coefficient of lift on a flat centerboard or keel is not good. It's a bad coefficient. It's not nearly as efficient as the curve of the sail. But the more important question I have for you is, why would they be the same? Compare the two fluids. Besides density, what's the big difference between air and water? What's a huge...
Friction?
Pardon?
Friction?
Well, yeah, but there's something that normally, it's the difference between pneumatics and hydraulics. Compressibility, right? Pneumatics are compressible, which is air or gas, and then hydraulics are normally water or oil, and that's considered incompressible. But why is it the same then for this? And this is just a thought question. I don't know if you're going to... see you guys, because I'm telling you that in the domain we're talking about, they operate the exact same way. In the domain we're talking about, those two fluids operate the same way. But they both operate as if they're compressible, or they both operate as if they're incompressible. What happens to air when I go like this? Does it compress through my hand? How come?
Moves out of the way.
How does it know you're coming?
With your hand.
It hears you.
Hears you.
When does air, it does. When does air in a free environment not hear you coming? Nope. Because it can't be heard that. Come on, in
Speed of
1947 we proved that it wasn't impenetrable.
Speed of sound?
Yes. That is the reason why the only time air in a free environment, not talking about inside a cylinder, the only time air is compressed in a free environment is if it doesn't hear you coming. Then it jams up in front of you and forms shock waves, sonic booms. Because otherwise, and if you look at the airfoil shapes for supersonic aircraft, if it was purely supersonic, but it has to transition to subsonic, if it was purely supersonic, it looks totally different. Sharp, razor sharp leading edges, not the nice little rounded front curve which you use for flow separation, because it's a totally different phenomenon. But the cool thing about it is, under sailing conditions, until you go supersonic, It is exactly the same phenomena. Air is incompressible unless it doesn't hear you coming. It just simply gets out of the way. And you'll observe this. If you ever see a float chamber or a smoke chamber when they have airfoils, you'll see that you put an airplane there or a car in there and you see the smoke starts getting out of the way before it gets to the airplane. You see it coming out of the way because it hears it coming. Oh, I gotta get out of the way. But if we're going supersonic, the smoke would impinge the thing and then say, oh, wow, didn't hear you coming. And then you get the compression shock wave. That's a fascinating thing. But it does mean this same formula does work, but we're using different densities terrifically. The area is going to be a lot smaller, but not 800 times smaller, because the velocity is going to be significantly less, unless you're going really fast. And then the coefficient of lift is quite a bit different. Now, by the way, if any of you folks have watched the Sail GP, or any of the hydrofoil suspended boats, you'll see that they get to a red zone at about 100 kilometers per hour, around 60 miles an hour. And what happens there is that, remember the speed of sound is much different in water than it is in air. You start getting bad things happening there in water. And you'll start getting shock waves and all sorts of things happen, and cavitation. And so there's this phenomenon that is kind of like the sonic barrier that happens in water at about 100 kilometers per hour, a little 60 miles an hour. And so that's been a practical limit, although we're slowly pressing up on that. Okay. We'll finish the physics, unless any questions about this for a while. Yep.
So when you say that it can hear your hand coming, so like
Okay.
vibrations or what?
Yeah, I mean, hearing is just vibrations, right? And so it means that if something is moving, it's generating a bow wave. And that we see some boats. I mean, it's generating a bow wave, and that bow wave then is in front of the boat, and until it no longer is. And so in the air, there's vibrations going forward because of that reaction. It said, oh, hey, I'm getting jammed here, and it tells the molecule next to it, hey, I see you're getting jammed. I'm gonna move out of your way. And so that kind of just progresses, and the faster you go, the less time there is for that to react until you get the speed of sound. And now then, there is no, you can't hear. I use that just kind of as a cute way of saying, here you're coming, but it's really sensing it's there. There used to be the old joke about, again, I spent 24 years flying in the Air Force, and the old joke about, when you have a tandem pilot, I mean, that's the reason that on the F-111, the co-pilot and pilot, navigator and pilot sat side by side, and that's so you go supersonic and hear each other. Because if you're front and back, the guy could never talk and hear the guy in front, right? Right? Oh no. Only if the air inside the cockpit was going supersonic. And of course, you have a canopy, so it's not going, no one could survive their face at supersonic speeds. It wouldn't be a matter of hearing, you'd have no face left. So, but anyway, okay, I'm sorry, that was over his. Okay, so now we're going to talk about sailing particularly, and about a famous circle. We put the boat in here, and this is the way the wind's blowing. And so these are called the points of sail. Okay, so there's lots of different ways that the boat could be sailing. For example, it could be sailing in this direction. And if it was sailing that direction, well, okay, wait a minute. It can be sailing. How high can it sail into the wind? What angle? Pardon? 45. 45 is a good number. We're going to use 45 degrees. Okay, so what it says that the boat could sail this high up into the wind, or it could go any direction here. You have to do something here, but it can go every direction this way here. So this is a sailable area. This is people call it in irons. It's no sailing. And so traditional sailboats cannot sail in this. In fact, almost no sailboat can sail in here. You can sail really close to the wind, but it's hard. Maybe you can go. You can maybe go to. This is at 45 degrees. You might be able to squeeze it 35 degrees if you want to pinch. They call it pinching. Maybe 25 degrees in some boats, but you're not going to get much better than 45 degrees. So there's points of, there's this point here, there's a point right down here, which is dead downwind. And then there's all these points from here to here. So, what is this point here called? If I was turning the boat and going straight downwind, what's that called?
A run.
A run, that's right. And so it is one of the points of sail. Okay, just for kicks, who thinks this is the easiest, safest way of sailing? Who thinks it would be?
Safest?
Yeah.
Safest.
It's not the safest, it's not the easiest, it's also normally the slowest. Except for this. But it doesn't take anything to do this. In fact, curiously enough, this is the only place where we don't use aerodynamic formulas at all. Because remember the lift is always generated perpendicular to the apparent wind, which means if we do develop lift, it's going to be this way, or this way. And so the only thing, if we're going straight downwind, the only thing we can rely upon really is drag. And so then we're not going to worry about that. Now, this point up here, or this point here, is called what?
Close haul.
Close haul. Which means it's as close as, it's not really as close as you can, but it's the smartest way if you want to make progress upwind. You can go a little closer than that. What is everything from here to here called? A reach. Now, if you're at the helm, it makes a huge difference whether you're reaching or close haul. Reaching really means, if you're at the helm steering the boat, that means you are going directly to a point. You are reaching to a point. If you're close haul, you're not moving to a point, you're trying to keep it on this knife edge at 45 degrees. If you're on a straight run, you're not going to a point, you are trying to keep the wind directly behind you. These 3 points are defined points based upon the wind direction. Anything other than that is not based upon the wind direction, but where you want to go. And so, if you're on a reach, that means, oh, I want to go over that corner there. So I adjust the sail so I'm going to that corner. It could be anywhere along here. This is a close reach, this is a beam reach, this is a broad reach. And so the reaches can be anywhere in here, but there's no distinct point. If we were going in this direction, well, first off, if I'm facing the bow of the boat, which is starboard, which is port? Which side is starboard? If this is the front of the boat, is this the starboard side or the port side? Why is that?
The starboard is right.
Well, why is it called starboard? You guys know?
It's the side for the steerboard.
Yes, and that was from where?
That was from when people used to direct the ship.
Yes, because before they had rudders, especially in the Viking days and the Scandinavian days, they would go upwind by rowers, and then they had big square sails for going downwind. And so they didn't want to have extra drag of a rudder. So when they would be rowing, or actually when sailing, they would take one oar and drop it over the side on the steering side. And it was heavy, the steering side, because this side is the side they came to dock with or came to port on. Because they always came to port on this side so they wouldn't damage the steering board, which is on this side. So that became known as starboard. Have you ever heard the term posh? What a posh place is this? It means really fancy. What does that mean? There's a P and an S in there. Port outbound, starboard homeward. That had to do with the way the ferries going across the English Channel would sell their cabins. Because as they pulled out of port, if you were on the port side, you have to see the royal family's residence, which meant port outbound. Coming back, starboard side of the boats once gets to see that. So the posh cabins were the ones that were on the port side, the viewing side, when you're going outbound, and of course it'd be reversed as you're going inbound. A little trivia for you, but posh, that's port and starboard are on there. Okay, so we have these two. We have this reach, and again, it's really important to understand that when you reaching is totally different than close haul to running, because reaching means, again, going to a point of sale, which means that, what it really means is that you set your rudder to go there, then you trim your sails to make the best there. In the other directions, you trim your sails high as they can, and then you use your rudder to maintain close haul or running. So in one case, the condition you're changing is the rudder, if you want to stay close haul or run. And on every other place, you should be controlling, the running control will be your sheet angles for your sails, because your rudder will stay fixed to where you want to go. If you're a crew on a sloop, which means two sails, and again, the crew in front would normally be handling the front sail, that means you never cleat a jib when you're reaching, because you're always adjusting it to make sure that it stays trim by observing the tails and what other indications you have in a particular boat. But if you're close haul, you're doing a disservice to the crew if you do not cleat the jib. Because that means if you're adjusting it, then the guy or the person who's controlling it is mostly controlling that wind angle by observing the head sail, by observing the tails, and if you're constantly moving that, then she or he will have no way of knowing whether they're close haul or not. So please understand that there's a huge philosophical and pragmatic difference between being on these points or anywhere else. Okay, is that clear? Which is the fastest point of sailing, by the way?
Beam reach?
Yep. Okay, now we're getting into something which is really cool. I think it's you can really enjoy this. And before, as an antecedent to this next topic, I'm going to give you. You can just pretend like you didn't hear this before. I'm going to give you a quick little quiz here, and this will show if you really understand what's going on here. This is a river, and it's flowing in this direction. It's flowing 5 knots. Two brothers, two sisters, identical capability. They know how to make the boat. They have the identical boat. They give a challenge to each other saying, listen, let's race from A to B, and you can pick any day of the week you want to do it, but we'll just see who has the fastest elapsed time from here to here. It's 1 nautical mile long. So, sister says, okay, I'm not working, I'm just going to pick a great day. And she waits and she waits and she waits, and there's no wind, no wind, no wind. And finally, she managed to pick a day when there's a 5-knot breeze finally blowing here. This is the sister. The brother, of course, is an industrious, and he works all the time. He only has 1 day that he can sail, and on that day, the brother has 0-knot breeze. Who wins? Who wins? The sister takes off with a 5-knot breeze in the direction she wants to go. The brother has to put the boat in the only day he's got left, and there is no wind. Who wins? And before you tell me this, you have to explain why. And tell me exactly the time of the loser.
From A to B.
Yep, from A to B. By the way, talk to one another. I taught RD 1001 for 15 years. First day of class, I used to always have a group question. You guys like the 1001? Do you like it? Did you like it?
I don't think
The question, I would give this question in first day of class saying, I believe in an active classroom, which means chatter and communications amongst yourselves and with me and all that. And so I would say, I'm going to flash that question here on the board. You're going to have 5 minutes as a class of 60 people to come up with the answer. And the answer must be correct for everybody in the room. And I said, are you guys ready? And the question flashed up says, and I would do it for you guys too. You could have the same question. How many Jingle Bell concerts have you been to? That's it. You got 5 minutes.
right now.
Yes, do it.
Not enough.
Aha! He's been there. So that is the only correct answer. And it encouraged people to talk about it. Because, oh, no, I've been to any, so the answer must be 0. And they said, you've been to 1. I said, well, I've been to 6. I would tell people. And that is not enough. And sadly, That's all they'll ever be. You mark it. Okay, so that's just to encourage people to communicate. So communicate now. If you think you know the answer, and sit for Alex. You're not allowed to play. Did you know this? What is it?
What?
Come on, get over here. Get over here and talk.
I don't know.
And let me tell you, it has to do with winds and understanding sailing.
This is specific to the
Oh, that's bigger than
What's up to do with sailing?
Ah!
Sailing, dude.
Yeah.
They're going down
brother.
They're identical boats, and they're both exactly as skilled.
Okay.
So first I thought it was a tie.
Okay, if ties, that's a legitimate answer.
Now I'm thinking.
But I do want you to know, in one of the cases, you can tell me exactly how long it takes. In one case. So you have to be able to tell me exactly how long it takes.
It's probably the brother.
Well, for the
the
sister,
apparent
there's
width
no
of the
apparent winner.
You have one more minute.
And for the brother, it's gonna be until
Oh.
they're getting back.
For the sister,
But you're flowing, you're going from A to B, you're going through path.
yeah. So if the boat's moving
Yeah.
A to B with the current and the wind is
Oh,
moving at the
I think
same
you
speed,
know
There's no.
there's no apparent winner.
Okay, that's an important point. You guys all catch that, right? Okay, go ahead.
So
Coming at you. So like, if there's no wind, you're like
So
hitting it, but if
she's
it's going
traveling at,
oh,
like, she's gonna be traveling at
Oh,
5 knots.
You guys have an answer yet?
no. Could it be a tie? Brothers.
I believe tie.
If there's no apparent wind, then
yeah,
The wind
that's
doesn't
the.
matter. Because for the brother, the apparent wind's just gonna be like upstream.
Oh yeah, you're right.
So
Yeah, because then the apparent wind would be 5 knots in the opposite direction, but then he can
He
just
would still be able to sit
he
on
can
it.
sail into it.
Yeah.
Because you can make your own winds basically.
How long is 1 nautical mile?
1.15 miles.
yeah,
it's
like
gonna be.
knots.
Well,
a
I-
knot
what-
is a
what's the-
nautical mile.
What's the definition of a knot?
1 nautical mile.
Per hour.
Yeah.
Okay.
Never say knot per hour, by the way. That's acceleration. And how long is a nautical mile? What's it defined as?
I believe it's 1.15 miles.
Okay, I want the definition.
It's
Uh,
a mile on water.
What is it?
Oh, I was gonna say, in between the latitude.
Yeah, it's like
Tell
a
me more.
second of a degree or something.
Yeah, I think it's.
A long way.
Along the equator.
Yes, only along the equator, which means it's at 2,160 nautical miles around the equator, right? So, but that's not the same. That's not what people use.
Yeah.
Because generally navigation we use as 1 minute of longitude.
Yeah.
We use it as 1 minute of longitude, but that's not really the case, because the longitude is not exactly that. So it's anywhere between 6,040 and 6,052 feet, depending upon where you do it. But most people use 6,000 feet, or 1.15.
Yeah.
Pi is 3. Okay, that's time's up. What's the answer? What's the answer? Come on. You've got to make a vote here. Everybody's got to vote. Start from here.
Are we going to
Yes.
I'm going tie, because that's what
Okay, here, Ty.
We're going on that, alright.
So like sister gets
What?
there in like a fifth minute.
Is the answer.
What is that?
Okay,
Sister wins. Okay, what do you think? Here we go.
Yeah, I think
Everybody just put it out here. We're going to say, we have, here's sister, Ty, and brother. We have 1 and 1. Give me some more time.
Tie.
Ty, Ty,
Sister.
sister,
Sister.
sister,
I'll go with brother.
brother,
I'll also go with brother.
brother,
Brother.
brother. Wow.
Just to tie it.
1, 2, 3, 4, 5. So it looks like you need to call an expert. You know, phone the expert. Okay, so those of you who said Ty, quickly give me why.
Because when they're going downwinds, the only thing that's affecting them is drag.
Thanks for playing. So, for those of you who think the sister one, tell me why.
So the sister is gonna have like no apparent wind, but the brother, if like the apparent wind for the brother would be like opposing him.
Oh, yes, absolutely.
But you can sail into it.
Wait a minute, you already said, what did you say before?
I said sister.
No, what did you say before?
I said brother.
Okay.
Well, I mean, yeah.
Okay. So what you said, okay, I got your explanation, thanks for playing. What do you say?
I think it's the brother because
Why?
everyone else is choosing the other ones. No. Cause
I got a hint here. Here's a pond with a leaf, and here is a boat. And the boat sees a 5-knot headwind. Can it leave that leaf? How? How can it leave the leaf?
it could turn off of the wind and then, yeah, it can tack up.
So,
Yeah.
in the case of the sister, the boat starts here, the leaf's right here, and they end together. Because they have no apparent wind, they're not sailing. That means whether the sail's up or not, they're a leaf. But the brother starts here with the same leaf. Initially, they're going together. But all of a sudden, now you see, he's looking down there, he doesn't look at the shore, he's looking at the leaf. He says, I have a headwind. I'm like this. Oh, I can sail. And so he tacks, and he beats the leaf. So this one takes 12 minutes. 1/5 of an hour to go 1 knot. This one takes less. What is this concept we're talking about here? Apparent wind. Awesome. That's exactly what we're getting to. Apparent wind is what, unless you're at anchor, no boat cares about the true wind. The only time you'll see true wind is if you're at the anchor or at a dock. Sailboats operate by apparent wind. So the next question I have for you, this is interesting, by the way. That was a nice little thing. Here we go. So now we're going to take a boat, and we're going to sail a course that's it's a square course. And we'll say the wind. I don't care. Let's say the wind's going this way. How many upwind legs are there? Okay. Someone tell me how many upwind legs are there? Okay. How many downwind legs are there?
One.
Everybody agree on that?
Oh, lazy. There's,
You guys forgot the leaf analogy all the way, didn't you? How many upwind legs are there?
That's a lot.
Oh, there's 4 legs. It's going.
Yeah, but that's.
I'm sorry. It's sailing from here to here, going here, going here, going here, and coming back to where it starts. It's a square course. It doesn't make a difference. I could be a circular course as far as I'm concerned. But I want to know what percentage of this course is going to be upwind, what percentage is going to be downwind. Based upon anything, we're saying that anything be from here to here, anything here, this is downwind, anything here is upwind. So what percentage is it? Come on, half and half?
Gonna be more upwind.
How much? How many legs, 4 legs, how many legs are upwind? 3 of them. That's what he says.
I'm down for 3.
Okay.
Yeah, you could get like percentages of it.
I think 75% is what you're going to find out.
Yeah.
This is a critical thing for you to all understand, is that if you're sailing, if you start from one location, come back to the same location, 3/4 of the time you're going to be sailing upwind because of your apparent wind. Now, the lighter the air is, the higher the percentage of times it will be that way. Because in light air, you have a radical shift in apparent wind. In heavy air, then it won't be so dramatic. But you will always spend more of your time upwind than downwind. And I guarantee if it's a square course, 3 of those will be upwind if it's directly into the wind. This is the reason why you can go anywhere you want to with a sailboat. If you can't go upwind, you are crap. You're not worthy. You are not worthy if you can't make a boat go upwind. So do not be the people who buy the Hobie 16s or the Hobie 14s or the other sport casts and just go back and forth across straight lines, back and forth all day because they like to go fast, because they don't know how to sail. And it's the same way with windsurfers, by the way, as opposed to sailboarders. You see windsurfers, you see the tracks just going back and forth, 30 miles an hour. That's all they do because they can't go upwind. The true test of a first successful sail for someone is when you can leave a place and get back to that same place when you sail. Do not be the person that says, "Oh man, I'm really a good sailor. Someone told me back." You don't want to do that. But there's a miscommunication that people think that, well, I'm only going to go upwind 1 leg, or this is the only. I mean, this would be. It looks to me like be a reach, which is really easy. This would be downwind, which is, a leaf does that, and this would be another easy reach. No, these legs are all going to be upwind because of the way the apparent wind shifts. So I got this cool little diagram. We got 8 more minutes here to talk about apparent winds. And I just discovered this because apparent wind is something which is not, it's a little non-intuitive. I mean, it is if you are a real vector person, I guess. But I've got this cool thing here.
I was thinking about that.
And it's a from an old sailing instruction book. If you take, let's imagine there's a 10-knot breeze, and let's imagine that our boat does 5 knots. And of course, and this is 10 knot. This is the wind. Okay. And so if I were to do some vectors here. If I were to draw a vector here, which represents. This is the boat here. This represents 5-knot vector. Gotta make sure I'm doing this right here. Yeah. Okay, and then I'm going to draw a 10-knot wind. Let's see, I'm going to draw that from. Yeah, I'm going to draw a 10-knot wind circle around. Let's see. Okay, here. Okay. We're just going to talk about one direction here. Okay, so now. Let's say that we want to go on a, the way to figure this out is that if the wind is coming from this direction here at 10 knots, if this is just a way of doing the vector addition in a kind of clever way. If I'm talking about a apparent wind angle of 45 degrees, which is, again, remember we said that was close haul, so that means, here's wind coming here, that means I want to go like this, where this angle here is 45 degrees. The actual apparent wind I'm going to see, if I'm sailing this way here, is going to be this way. And so this is going to end up, if you look at this ends up being about 30 degrees. And so that means when you're sailing a true angle of 45 degrees on close haul, what you'll observe on the boat is 30 degrees. And by the way, if this is 10 knots, what is this? Quite a bit more. In fact, you look at that out, you'll find that this is going to be 13.7 knots. So, in a 10-knot breeze, if I'm sailing close haul, I'll be seeing almost 14 knots. But I won't see it at 45 degrees, I'll see it at 30 degrees. And this is the reason why people often get confused, because you're expecting to see 45 degrees on your wind vane when you're close haul. But you should see like 30 degrees. Because your true angle, if you look at your compass, would be 45 degrees. But because of the shift in the apparent wind, because the wind was at 10 knots from here to here, but now that we're adding our vector to it, it ends up being 13.7 knots from a different angle. Now, look at the beam reach. The beam reach would be when you're sailing at a 90-degree angle. So here we are. This is 90 degrees now, which would be a beam reach. But the apparent wind is here. And in fact, the apparent wind, if I did the calculations here, yes, on a beam reach, this is going to be now about 11.1 knots. So it's still, your forward vector does increase from the 10 knots that was here that we started with. But notice that the angle here that we're sailing at is 65 degrees. So a true beam reach on a sailboat, and by the way, everything we saw in the wind circle is based upon apparent wind. So if you beam reach starboard and beam reach port, they're not going to be 180 degrees apart from each other. They'd be 130 degrees apart. It's only 65 degree apparent wind in this particular situation gives you 90 degrees from the real wind. And so a beam reach, when you're actually at 90 degrees apparent wind, 90 degrees in the true situation is actually only going to be 65 degrees is what you'll see on board the boat. Okay, and so what happens if you go straight downwind? First off, how much wind do you feel? In this situation where you have 10-knot wind, 5-knot plus 2.
You feel the wind minus your boat speed?
Yeah, which is 5 knots. And of course, it will be directly 0 degrees. I mean, it's not direction. Now, how many boats will go 5 knots in a 5-knot breeze? Not any. Because remember, you're relying upon drag. And so you cannot, that would be 0 drag if you could do 5 knots in a 5-knot breeze. So the bottom line is that this is much more exaggerated because 5 knots boat speed depends upon whether it's going to be, it sees 13 knots, whether it's going to see 11 knots, or in this case here, it only see 5 knots. Now, we said 3/4 of the time you're going upwind, which means you're somewhere in this, 11 to 13 knots, and then you go downwind, what happens? You said, oh my God, the wind just stopped. No, it's the same wind, except that on this leg here, it's going straight downwind. It'd be by far the slowest sail, because your speed subtracts from the real speed, and the apparent wind goes to almost nothing. And yet, in this leg here, you're going to have 13.7 knots. And again, remembering that it's a V-squared phenomenon, which means you're going to develop almost 9 times more force on the sails. This is the reason why you have to hike like a heck to go upwind, and yet going downwind, you feel like, oh my God, we lost all the breeze. No, you didn't. You're subtracting from it. And so, and it's also the reason why boats that really want to go well downwind will have additional sails to put up. On most boats which have the big downwind sail spinnakers, they will double the sail area when they go down. On my 470, the spinnaker is 140 square feet, and the working area is 140 square feet. So you double the sail area, which again makes the forces better because that's a linear thing, unfortunately, whereas velocity is a squared phenomenon. And so the apparent wind thing is really, really important to see because people get confused all the time. You look at the wind vane or you look at the wind vane on top of the mast. Oh my God, I'm on a beam reach. No, if it shows you're at 90 degrees, you are not at a beam reach. You're below a beam reach. You have to be sailing at 65 degrees in this situation with 10 knots of breeze in order to actually be traversing beam to the true wind direction. Okay, I keep talking about, we talked about tailtails, which is a way to tell whether the sail is trimmed or not. We have those on sailboat, if you notice. I have a couple of stripes on the wing there. But it doesn't tell you what point of sail you're on. For beginners, I don't know how people sail without it. Every boat I've had has had a spar fly. Spar fly is a wind vane on top of the mast, out of the interference of the wind. You can have them on your shrouds, but it's not as accurate. It's more of a relative wind. Then you have it on top, and you're likely to get a true wind direction, or not a true apparent wind direction, which is uninfluenced by the sails. When I teach people to sail, I always have boats which have it on there because it's the first thing I tell people, look and see. Are we reaching? Are we running? Are we close haul? Look at that. And because otherwise you can start sails and you can sail in circles, forgetting which direction you're going. Just try to keep track of the trim tabs and all that. Anybody sail with a spar fly? On big boats, and again I think we mentioned this last week, is that big boats don't teach you the same sailing that you need in a small boat. Small boats are much more reactive. If you can learn how to sail a small boat, then going to a big boat is easy, not the other way around. Big boats, it's really hard sometimes to tell what's happening, so almost every big boat that I've ever been on will always have a spar fly on top, often with 2 different illuminated indicators which say what is that 45 degrees. And they'll have them from the top. The reason why most dinghies don't is because they get damaged every time you capsize. So that's all I wanted to cover today. I wanted to get you out of here at the time it's supposed to be. Next week we will be talking about, actually we're talking about more of the nuts and bolts of boats and talk about the parts and types of sailboats, a bit of that. Any questions about what we talked about? There will be a quiz, by the way, at the end of the term.
Okay.
I have the privilege of doing this since I'm officially going to be giving a grade to you guys. So if you have any questions, let me know. And there we go. We'll also be doing some knots and ropes, some of the basics that you don't know. I just learned, by the way, anybody know, we all know the Kristen knots, right?
The what?
The Prince of Knots.
I don't know.
The Prince of Knots.
Square knot?
The Bolin.
Bolin? Yeah, Bolin's pretty
Okay, but I just discovered today how that was named.
cool. Is it bow line? I assume it's
It was a
bow.
bow line
I'm assuming
from
it's bow
what?
line related.
You know, I mean, we'll talk about this a little later, but square riggers truly could go upwind slightly. Because even the square rig boats had a 4 triangular sails on the front, and they used to have a mizzen in the back that was also triangular sails. So they could go like 15 degrees into the wind. In order to do that, they had to crank over the yards, which are the thing that holds up the square sails, crank them up toward the bow so they get them at angles. The thing that they had on that were called the bow lines. The bow lines were the lines that pulled the yards forward so you could actually attempt to go windward. And the knots they used on them were the special knots for bow lines, which became a bowline. And then we know that halyards were also named for the same square rigging thing, hauling yards. The yards for that. So there's a lot of sailing trivia that enters into communications, but the posh one, I think we should always remember. All right, thanks guys.
Thank you.
Yep. Sure.